After World War II, Japan National Railways, JNR, faced challenges due to coal shortages and shifted towards utilizing electricity generated from hydroelectric power. At that time, electrification was primarily done using direct current, DC, but construction costs became a significant barrier. While major trunk lines could justify the enormous investment, the need for electrifying regional lines increased as electrification expanded. To address this issue, alternating current AC electrification gained attention. In 1953, Showa 28, the AC Electrification Research Committee was established. In Europe, various electrification systems were being tested, and among them, France's commercial frequency AC electrification caught Japan's attention. Although Japan sought technical cooperation with France, the conditions between the two countries did not align, leading Japan to pursue AC electrification using domestic technology. As introduced in another video, various rolling stock were developed and tested, but the electrical system consistently used was single-phase AC at 20 kilovolts. Compared to the 1,500 volts used in DC electrification at the time, this was more than 10 times the voltage, requiring different insulation measures than those used in the DC era. However, the high voltage brought other advantages. When running a train with the same power consumption, the current flowing through the overhead line decreases in inverse proportion to the voltage, so there is no need for the large current seen in DC electrification. The current is reduced to less than 1/10, allowing for thinner overhead wires and feeder lines, and less voltage drop in the overhead line, resulting in stable performance. This feature of reduced voltage drop had a significant impact on reducing construction costs. It allowed for wider spacing between substations, meaning that the number of substations required in an electrified section could be greatly reduced. The mercury rectifiers used for DC conversion at the time required troublesome maintenance and temperature control, so eliminating them was another advantage. AC electrification seemed beneficial in terms of ground equipment, but the 20 kV high voltage posed a challenge for the rolling stock. It was necessary to convert the high voltage from the overhead line to a low voltage usable by the motors, and furthermore, to drive DC motors, those troublesome mercury rectifiers had to be installed in each vehicle. Attempts were made to use motors that could run on AC to avoid mercury rectifiers, but these efforts failed. Coinciding with this, the rapid advancement of semiconductor technology made its application to power equipment possible. The widespread use of silicon rectifiers solved the rectification problem, and the shift to DC motor drive proceeded rapidly. Initially, silicon rectifiers were expensive and had small capacities, but they gradually became cheaper and more powerful, leading to their widespread adoption even in high-power applications like railway vehicles. With the practical implementation of AC-powered rolling stock, electrification across various regions proceeded rapidly using the AC system. However, the situation where major metropolitan areas were already electrified with DC, while regional main lines were electrified with AC, led to new challenges. At that time, numerous long-distance trains were operating, connecting local cities with the Kanto and Kansai regions. For locomotives, the issue could be addressed by switching from DC to AC locomotives, but this process was time-consuming and labor-intensive. For EMUs, it became necessary to develop AC-DC dual-system EMUs capable of running on both AC and DC sections. Eventually, AC-DC dual-system trains became the standard for both locomotives and EMUs. However, this required adding transformers and rectification equipment, which are typically housed in substations, directly onto the train. This added considerable weight to the trains. Transformers and filters for managing rectified current are essentially heavy blocks of copper and iron. For EMUs, the transformer alone weighs over 3 tons and is required for each unit, which negates one of the key advantages of EMUs, their lightweight design. Additionally, in DC sections, this equipment becomes nothing more than dead weight, providing no benefit at all. Increased weight leads to reduced performance and places a greater burden on the tracks, potentially increasing maintenance costs. There is a story from the JNR era that the 181 series was the best EMU for drivers, and one of the reasons for this can be attributed to the weight increase of later models. Additionally, in DC sections, the EMU could receive ample power from the overhead catenary and exhibit high output at high speeds. However, in AC sections, the transformer capacity became a limiting factor. At the time, DC EMUs could produce outputs far exceeding their rated capacity because they had sufficient power supply from the catenary. To reduce weight, J&R's dual-system EMUs did not carry transformers with enough capacity to deliver the same output as in DC sections. AC sections often comprised regional lines where high performance was not as critical, leading to a decision that the cost-effectiveness of installing higher capacity transformers was low. As a result, in AC sections, the full field speed at the final notch was limited, and acceleration performance at high speeds was capped. This would have been particularly frustrating for suburban and express trains with high gear ratios. It was as if they were struggling with the same phenomenon experienced by long EMUs on local lines, where significant voltage drops in the catenary impeded acceleration. The issue of heavy transformers is still unavoidable for vehicles that handle AC power today. Although advancements in materials and design technology have led to lighter transformers, there are limits to weight reduction due to the unchanging basic structure of transformers. For example, in the Shinkansen, the main transformer in the 0 series had a capacity of 1650 kV/A and weighed 3.5 tons. By the time of the 300 series, the transformer capacity had increased to 2,900 kV/A, but the weight had decreased to 3.06 tons. This represents a 1.7 times improvement in capacity per unit of weight, showing progress in weight reduction, though the transformer still weighs over 3 tons. Even though further reductions in weight continue to be made, reducing the weight by even 10% has proven to be a significant challenge. AC electrification allows for the supply of large amounts of power, making it suitable for high-speed vehicles that demand high output. In high-speed trains, weight reduction has become increasingly important to reduce energy consumption and track wear. As we enter the 21st century, there has been growing attention on technologies that could enable the lightweighting of transformers. In Europe, where low-frequency AC electrification, such as 16.7 Hz, is prevalent, the transformer weight issue is even more critical than in Japan. The ultimate solution for reducing weight seems to lie in high-frequency AC systems. As explained in a previous video regarding the increase in motor speeds, raising the supply frequency allows for the reduction of transformer core material and fewer coil windings, while maintaining the same performance. However, increasing the frequency presents significant challenges. Advancements in semiconductor technology have made frequency conversion much easier. Moreover, with the mass production of dedicated control chips, the complexity of assembling and adjusting circuits is no longer necessary. A common example of this technology in use can be seen in PC power supply units. In PCs designed for gaming or graphics-intensive tasks, it's not uncommon to find power supplies with a capacity of 1 kilowatt. Despite this, the power supply fits comfortably within a standard PC case. If traditional transformers were used, the power supply would be large and heavy, making it difficult to carry. However, PC power supplies are small enough to be carried with one hand. This is because the transformer operates at a high frequency, making it compact and lightweight. The AC from the power outlet is immediately rectified by a rectifier, converting it to a nearly DC state before being sent to the inverter circuit. The inverter then produces high-frequency AC, often above tens of kilohertz, which is sent to the transformer. As a result, the transformer becomes very small and light, weighing only a fraction of what it would otherwise. The desire to achieve the same for railways naturally emerged. However, in the case of railways, the AC power supply voltage is exceedingly high, exceeding 15 kilovolts. To handle this, semiconductor devices capable of withstanding high voltages are required, which remains the biggest bottleneck even today. Additionally, semiconductors that perform switching operations do not transition from the on state to the off state instantaneously. There is a brief intermediate state. This is akin to having electrical resistance, resulting in heat loss. To miniaturize and lighten transformers, high frequencies are necessary, requiring rapid and frequent on-off switching. If there is electrical resistance each time, the higher the frequency, the more heat is generated. This reduces the efficiency of the converter, and the heat sink becomes larger, counteracting the miniaturization efforts. The advantage of conventional transformers is that they provide electrical isolation between the input and output sides and have minimal losses when changing voltage and current. Their conversion efficiency exceeds 96%, making them exceptionally efficient among classic electrical devices. To approach this level of efficiency, various innovations have been made to shorten the time required for switching between on and off states. However, improvements in silicon materials have their limits, leading to the adoption of new materials like silicon carbide and gallium nitride, which differ from traditional power semiconductors. Though still facing cost-related challenges and not yet widely adopted, these materials are considered the most promising components. If high-speed, high-voltage switching devices made from these materials become widespread, a new era for AC-powered vehicles will begin. After all, it would usher in a time where the long-standing issue of transformer weight could be nearly disregarded when designing vehicles.